Hey everyone. Before we dive into this amazing story about how a dream led to the creation of the periodic table, make sure to hit that like button and subscribe to stay updated with more fascinating content. Now, let's get comfortable. I'm dimming the lights so you can fully immerse yourself in this incredible journey. Let's begin. Long before the word chemistry was ever spoken in a laboratory, human beings were already captivated by the materials that made up their world. Ancient civilizations wondered what everything was made of, from the stars in the night sky to the ground beneath their feet. They were curious, imaginative, and sometimes wildly wrong. But their curiosity set something powerful in motion, the long and winding journey that would eventually lead to our modern understanding of matter. Thousands of years ago, the earliest thinkers and natural philosophers believed the universe was composed of only a few essential elements. In ancient Greece, the philosopher Empedocles proposed that all matter was made from just four basic substances: earth, water, air, and fire. His idea was expanded by Aristotle, who added a fifth element called aether, a divine, invisible substance, thought to fill the heavens. It might sound quaint or even amusing now, but these ideas dominated scientific thinking for over 2,000 years. They weren't just beliefs, they were the framework for medicine, philosophy, and natural science throughout much of Europe, the Middle East, and Asia. People didn't test these ideas with experiments, they accepted them because they fit with how the world appeared. Fire felt energetic, water flowed, earth was solid, air was invisible. It seemed to make sense. As time passed, some began to question these old assumptions. Around the first few centuries CE, a mysterious and often misunderstood practice emerged: alchemy. This was a time when science, religion, magic, and philosophy blurred together. Alchemists were part philosopher, part chemist, part magician. They experimented with metals, minerals, and plant materials, driven by a few ambitious goals: to turn base metals into gold, to discover a universal solvent that could dissolve any substance, and most famously, to find the elixir of life, a potion that could grant immortality. Although none of these goals were ever fully realized, the work of alchemists wasn't in vain. Through their trials, errors, and endless curiosity, they developed the tools and techniques that would become essential to modern chemistry. They invented glassware, documented chemical reactions, often in coded language, and laid the groundwork for the idea that matter could be transformed. During the Islamic Golden Age, between the 8th and 14th centuries, Arabic scholars preserved and expanded upon Greek alchemical texts. Figures like Jabir ibn Hayyan, often called the father of chemistry, introduced systematic experimentation to the craft. In Europe, during the medieval and Renaissance periods, alchemy continued to flourish. Even Isaac Newton, one of the most brilliant minds in physics, dabbled in alchemy, writing hundreds of pages on the subject in secret. But by the 17th century, the winds of change were beginning to blow. The scientific revolution brought a new way of thinking. Scholars began to emphasize observation, measurement, and reason over mystical explanations. The four-element model slowly began to unravel. Fire, for example, couldn't be an element if it could be extinguished. Air wasn't a single thing, it was a mixture of gases. Water could be split into hydrogen and oxygen. Earth, that was too vague to be useful. In the 18th century, scientists began discovering true elements, substances that could not be broken down into simpler substances by chemical means. Thanks to pioneers like Antoine Lavoisier, the father of modern chemistry, the definition of an element became clearer. Lavoisier created one of the first modern lists of elements, identifying over 30 substances, including sulfur, phosphorus, and mercury. He helped demolish the idea of the four classical elements and introduced a new rigorous approach to studying matter. By the 19th century, the world was in the midst of a scientific transformation. New elements were being discovered at a rapid pace: oxygen, hydrogen, carbon, chlorine, calcium, and many more. These discoveries thrilled scientists but also overwhelmed them. By the 1860s, more than 60 elements were known. Each had its own properties, but no one could figure out how they all fit together. Chemistry was becoming a vast library of facts with no index. Some scientists tried to find order. They noticed patterns. Certain elements reacted similarly. Some formed compounds in predictable ways, and certain weights, what we now call atomic weights, appeared to increase in regular intervals. But the patterns were inconsistent. The more elements they discovered, the more confusing it became. It was like assembling a massive jigsaw puzzle with dozens of missing pieces and no guiding picture. Many tried to make sense of it. Johann Dobereiner grouped elements in threes, triads, based on similar properties, such as lithium, sodium, and potassium. John Newlands proposed the law of octaves, where every eighth element seemed to behave similarly, like musical notes. But these systems didn't work for all elements, and critics often dismissed them as coincidence or wishful thinking. Still, the idea was there, a hidden structure, a natural order waiting to be uncovered. And this is where the story of Dmitri Mendeleev begins. Born in Siberia in 1834, Mendeleev would grow up to become one of the most brilliant scientific minds of his generation. He believed that the chemical elements were not random, that nature, as chaotic as it seemed, followed rules. He trusted that if you studied it long enough and hard enough, a pattern would emerge. And he was right. But how he found that pattern, how he created the periodic table, one of the most important tools in all of science, was as surprising as it was mysterious. As we will soon see, the moment that changed everything didn't come in a lab or through endless calculations. It came in a dream. The story of extinction, while tragic and often overwhelming, is not only a story of loss, it is also a story of choices, human choices, and the possibility of transformation. The mass extinction unfolding today is not an inevitability. It is the result of systems, behaviors, and values that can be changed. We are not powerless. If we are the primary cause, we can also be the primary solution. Preventing extinction does not rely on a single silver bullet. It requires a symphony of solutions, working together across scales, local, national, and global. It demands science, policy, ethics, and community, all working in harmony. And it begins with understanding that conservation is not about protecting nature from people. It's about reshaping how people live with nature. One of the most effective tools we have is the creation and management of protected areas. National parks, marine reserves, and biodiversity corridors help safeguard the habitat species need to survive. The global target, recently reaffirmed in the Kunming-Montreal Global Biodiversity Framework, is to protect 30% of Earth's land and oceans by 2030. Known as 30 by 30, this target is ambitious, but achievable if countries follow through with action and ensure protection isn't just on paper. But it's not only about how much land is protected, it's about how it's protected. The best outcomes often come when local communities and indigenous peoples are involved as stewards. Many indigenous territories are rich in biodiversity, and these communities have maintained sustainable relationships with ecosystems for centuries. Empowering these groups with land rights, legal protection, and resources is not only ethical, it's ecologically smart. Another critical strategy is restoration. Damaged ecosystems can recover, forests can regrow, wetlands can be revived, coral reefs can be nurtured back to health. Rewilding initiatives are bringing back lost species and reintroducing keystone animals to revive entire ecosystems. In Europe, bison roam again. In Argentina, giant river otters have returned. The Earth is more resilient than we often give it credit for. We also need to address the drivers of extinction at the source. That includes reducing habitat destruction, especially for agriculture. This means promoting sustainable farming practices, reducing food waste, and shifting toward diets that require less land and fewer inputs. Intensive monocultures and deforestation for soy or beef production, for example, are major causes of biodiversity loss in the Amazon and beyond. A more diversified, regionally adapted food system could feed the world while sparing space for nature. Combating illegal wildlife trade is another essential step. Poaching for ivory, horns, skins, exotic pets, and traditional medicine continues to drive species toward extinction. Strengthening enforcement, improving global cooperation, and reducing demand through education and alternatives can help stop this global industry. Technology, such as DNA forensics and satellite tracking, is giving conservationists new tools to fight back. Pollution control, especially reducing plastic, pesticide, and industrial waste, plays a critical role in protecting both land and marine species. Innovations in biodegradable materials, improved waste management, and tighter regulations can limit the damage we do to ecosystems every day. We must also combat climate change, not just for ourselves, but for every species that shares the planet. Climate action is biodiversity action. Slowing global warming will help stabilize ecosystems, reduce habitat shifts, and give species time to adapt. This means reducing emissions rapidly, protecting carbon sinks like forests and peatlands, and investing in renewable energy and green infrastructure. Then there's science and monitoring, the foundation of informed action. We can't protect what we don't understand. Continued investment in field research, species discovery, and population monitoring is essential. This includes using citizen science platforms, AI-powered tracking, and satellite imaging to detect trends, identify at-risk areas, and measure conservation success. One of the more powerful yet underutilized tools is legislation. Laws can compel action and ensure accountability. The US Endangered Species Act, for example, has helped prevent the extinction of dozens of species, from the bald eagle to the gray wolf. Similar laws around the world, when properly enforced, provide a safety net for the most vulnerable. But policy alone isn't enough. Preventing extinction also means shifting cultural values. In many societies, biodiversity is seen as optional, as a luxury or a decoration. We need a new narrative, one that treats nature not as a backdrop, but as a co-creator of life. This involves education, media, art, and storytelling. It involves raising children to recognize the calls of birds, the names of plants, and the idea that other species are not just objects, but fellow travelers on this earth. Technology can also play a role. Gene banks and conservation breeding programs are preserving genetic material of endangered species. In some cases, de-extinction efforts are exploring whether certain extinct species could be revived. These are controversial, ethically complex, and not a replacement for preventing extinction in the first place, but they point to the potential of biotech in conservation science. Importantly, urban environments can be part of the solution. Cities can become sanctuaries, with green roofs, native plant corridors, and biodiversity-friendly planning. Urban conservation may not save tigers or elephants, but it can support pollinators, birds, bats, and amphibians. It also connects people to nature, which is essential for building the will to protect it. Finally, there's the matter of hope. Hope is not passive, it is not pretending things are fine. Hope is the belief that with effort, things can get better, and the motivation to act accordingly. It means recognizing that we are at a crossroads, and choosing the path that leads toward a livable planet for all. Yes, extinction is real, and it is happening, but it is not inevitable for every species at risk. With enough knowledge, resources, and will, many can still be saved. The giant panda, the mountain gorilla, the California condor, all once symbols of hopeless decline, are now symbols of what's possible when people care, coordinate, and commit. The biodiversity crisis is in the end a mirror. It reflects the systems we've built, the priorities we hold, and the future we choose. It challenges us not just to protect animals and plants, but to protect the planet's capacity for wonder, balance, and resilience. This is not just about extinction, it is about survival, of ecosystems, of humanity, of hope itself. We still have time, but not forever. To understand how one man could dream up a system that would reshape science, we first have to understand the man himself. Dmitri Ivanovich Mendeleev was born in Tobolsk, Siberia on February 8, 1834, the youngest of between 14 and 17 children, depending on the record. Even his birth was cloaked in uncertainty, just like the scientific world he would one day organize. Life in Siberia was harsh, cold, and remote, far from the cultural and academic centers of Russia, but even in this icy frontier, a fire had been lit, and it burned in young Dmitri. His father, Ivan Pavlovich Mendeleev, was a teacher of fine intellect, but he went blind when Dmitri was just a child and died soon after. The family's fortunes collapsed. The weight of survival fell upon his mother, Maria Dmitrievna, a woman of extraordinary will and resilience. Determined that Dmitri, her youngest and most promising child, would have an education, she made a decision that would shape history. She packed up their belongings and took Dmitri on a 1,000-mile journey to Moscow, hoping to enroll him in university, but Moscow turned them away. Undeterred, she pushed on to St. Petersburg, the intellectual heart of Russia. There, her perseverance finally paid off. Dmitri was accepted into the main pedagogical institute, the same school where his father had once studied. It is said that shortly after Dmitri entered, his mother died. She had fulfilled her purpose, and she was gone. He would later say, "She gave me the sacred pledge, go and find knowledge," and he never stopped. In St. Petersburg, Mendeleev studied relentlessly. He was brilliant, but also intense, eccentric, and stubborn. He wore long, unkempt hair and had a powerful presence. He wasn't always easy to get along with, but his passion for knowledge was undeniable. He completed his studies, began teaching, and quickly rose through the academic ranks. But Mendeleev didn't want to just teach chemistry, he wanted to rewrite it. At the time, chemical knowledge was scattered and inconsistent. There were dozens of known elements, and an even greater number of theories about how they should be classified. Mendeleev grew increasingly frustrated. He wanted order, structure, meaning, and he believed nature itself had a system. It just hadn't been uncovered yet. In 1860, he attended the first International Chemistry Congress in Karlsruhe, Germany. There, scientists from across Europe debated how to standardize atomic weights and symbols. The meeting planted a seed in Mendeleev's mind. It wasn't just that the world needed a better way to organize the elements. It needed a unifying language of chemistry, one that could transcend borders and theories. Back in Russia, he started working on a comprehensive textbook titled Principles of Chemistry. He believed it was impossible to teach chemistry properly without giving students a way to understand how elements relate to each other. So, he began his great experiment, not in a lab, but with a stack of index cards, one for each element. On each card, he jotted down everything known about the element: atomic weight, density, compounds it formed, reactivity, and more. Day and night, he shuffled these cards like a man obsessed, and in a way he was. He arranged and rearranged them, trying to find a pattern that made sense. He believed that somewhere, hidden among the facts, there was a structure that nature had already written, a structure only he could read. He was methodical, but also intuitive. He wasn't afraid to break rules or challenge assumptions. If two elements didn't fit neatly into the weight-based order, he would trust their behavior instead. If an atomic weight seemed off, he sometimes suggested it had been measured incorrectly, and many times, he turned out to be right. Then came the moment of insight. The dream. Mendeleev later recalled, "In a dream, I saw a table where all the elements fell into place as required. Awakening, I immediately wrote it down on a piece of paper." It's easy to romanticize that moment, a single dream delivering a scientific revolution. But the truth is, Mendeleev had been preparing for that dream for years. The dream was a spark, yes, but the fuel was a lifetime of study, instinct, and tireless effort. What he wrote that morning was the periodic table, a chart that organized the elements by increasing atomic weight, placing those with similar properties into vertical groups. For the first time in history, the chemical elements weren't just a list, they were a pattern. What made Mendeleev's table revolutionary wasn't just its structure, it was its predictions. He left intentional gaps in the table where no known elements fit. Most scientists would have assumed the table was incomplete or flawed. Mendeleev didn't. He boldly claimed that those empty spaces were waiting for elements that had simply not yet been discovered. And he didn't stop there. He predicted their properties, atomic weight, density, behavior, in astonishing detail. He even named a few of them using a placeholder prefix: Eka silicon, Eka boron, Eka aluminum. It was as if he was seeing the future. His ideas were not immediately accepted. Many scientists were skeptical. A few praised the attempt but doubted the predictive claims. But over the next 2 decades, nature began to catch up to Mendeleev's vision. When gallium was discovered in 1875, it matched his predicted Eka aluminum almost exactly. Then came scandium, and later germanium, all behaving just as he had described. The scientific world was stunned. Mendeleev had not only revealed the structure of the known world, he had foreseen the unknown. He was honored across Europe. He received awards, honorary degrees, and nominations for the Nobel Prize, though controversially, he never won it. Some say it was politics, others say it was rivalry, but Mendeleev didn't seem to care much about trophies. He cared about the truth, the structure beneath the surface. Even late in life, Mendeleev kept challenging the scientific norms of his time. He developed a fascination with gases, wrote papers on weights and measures, and explored the boundaries of physics and chemistry. He was appointed director of the Bureau of Weights and Measures in Russia, and even helped standardize the country's currency system. And yet, despite all his accomplishments, it is the periodic table that became his greatest legacy. It's hard to overstate its importance. The table is not just a list of substances, it's a map of matter itself, one that every chemist, physicist, biologist and engineer relies on to understand the building blocks of the universe. From hydrogen to uranium and beyond, the periodic table stands as one of the most powerful tools in the history of science, and it came from the mind of a man who saw the world not as a set of fragments, but as a unified whole. Dmitri Mendeleev died in 1907, at the age of 72, but his table lives on, updated, expanded and refined, but still echoing the structure he first envisioned more than 150 years ago. In the next chapter, we'll look more closely at what made his table work, the laws of chemistry he uncovered, the order he brought to chaos, and how his predictions turned from dreams into discoveries. Science is often thought of as cold, logical, and grounded in hard evidence, and much of it is. But history reminds us that behind the most profound discoveries, there is often something more, something that blends logic with intuition, data with imagination. That's exactly what happened in one of the most legendary moments in the history of chemistry, when Dmitri Mendeleev dreamed the periodic table. It was early 1869. Mendeleev was deep in the process of writing a textbook, Principles of Chemistry, and had become increasingly frustrated by the chaos of chemical knowledge. The elements, over 60 of them, seemed to defy any attempt at neat classification. There were patterns, yes, but no one had been able to lock them into a system that explained why the elements behaved as they did, or how to predict the behavior of the ones yet to be discovered. He had tried everything, grouping elements by atomic weight, by reactivity, by the kinds of compounds they formed. He made hundreds of notes, scribbled observations, tested theories, and most famously, began writing the properties of each known element on individual index cards. Each card included data like the element's atomic weight, its chemical formulae, physical state, and its affinity for other substances. Then he spread the cards across his desk and began trying to assemble them, like a puzzle with no reference image. He worked for days. His eyes grew tired. He skipped meals. His thoughts spun in circles. Again and again, he rearranged the elements, hoping the truth would reveal itself. but it didn't, until he fell asleep. According to Mendeleev himself, he had a vivid dream that changed everything. Later, he described the moment simply: "In a dream I saw a table where all the elements fell into place as required. Awakening, I immediately wrote it down. Just like that, the chaos began to organize itself. It wasn't magic, it was the result of long hours, years of study, and a mind already saturated with data." His subconscious had simply taken the baton where conscious thought had stalled. When he awoke, he took pen to paper and quickly sketched what he saw. The result was the first coherent draft of the periodic table, a grid-like structure in which the elements were arranged not just by atomic weight, but also by shared chemical properties. These properties repeated in a regular pattern. They were periodic, and the vertical columns of his table grouped elements with similar behavior: the alkali metals, the halogens, the noble gases. But perhaps the most revolutionary part of Mendeleev's table was not what it showed, but what it didn't. He left gaps. Where the known elements couldn't produce a smooth progression in properties, he left a space. And rather than treat these as mistakes or omissions, he made a bold prediction: the elements that belonged there had not yet been discovered. He didn't just say, "There's something missing here." He went further. He described the future elements in detail: their atomic weights, their densities, the types of oxides they would form, even their melting points. It was like predicting the characteristics of a new planet before it was even observed. This was not guesswork. It was not speculation. It was a declaration that nature followed laws, that the universe was not random, but ordered. Among the most famous of Mendeleev's predictions was the element he called Eka aluminum. Eka was Sanskrit for one, and he used it to mean the element one spot below aluminum. He predicted this unknown element would have an atomic weight of around 68, be a soft metal, and have a density around 6.0 grams per cubic centimeter. 6 years later, in 1875, French chemist Paul-Émile Lecoq de Bois-Baudran discovered a new metal in a zinc ore sample. He named it gallium. It had an atomic weight of 69.7, a density of 5.9, and matched nearly every property Mendeleev had described. The scientific world was stunned. 2 more discoveries followed: scandium in 1879 and germanium in 1886, matching Mendeleev's predictions for Eka Baudran and Eka silicon. The gaps he had envisioned in his dream were not errors. They were windows into the future. His table, once doubted, was now vindicated. It was no longer just a clever way to arrange elements. It was a predictive tool, a scientific compass that could guide the search for knowledge. His dream had become a law of nature. But perhaps the most fascinating question is this: what made that dream possible? To dream something meaningful, the mind must first be filled with meaning. Mendeleev wasn't randomly assembling images in sleep. He had immersed himself in the elements for weeks, memorizing them, arranging them, thinking about their relationships. The dream didn't invent the table, it unlocked it. In many ways, the dream was not just about chemistry, it was about how breakthroughs happen. Sometimes, the biggest leaps in understanding don't come from crunching more data, but from stepping back, letting the mind wander, connect and synthesize. Dreams, after all, are how the brain makes sense of what we can't explain when we're awake. Mendeleev understood that science isn't always a straight line. It's a conversation between logic and inspiration, between what we know and what we believe could be true. After the table was published and its predictions confirmed, Mendeleev's fame spread far beyond Russia. He received medals and honorary degrees from institutions all over Europe. His table would go on to form the foundation of modern chemistry, eventually expanding to include over 100 elements, from hydrogen to the synthetic super-heavy elements discovered in the 20th and 21st centuries. And still, its core structure, the one he saw in a dream, remains intact. Today, the periodic table hangs in every chemistry classroom. Scientists consult it daily, students memorize it, print it on mugs and t-shirts, and yet few realize that it was born not just from hard data, but from a moment of quiet, a mind at rest, a spark in the dark. It reminds us that sometimes science sleeps, and when it dreams, the world changes. Every great discovery leaves behind a trail, not just of what has been found, but of what has yet to be revealed. In Mendeleev's periodic table, those trails were the gaps, silent placeholders in a chart that otherwise brought harmony to chaos. But to Mendeleev, those blanks were not failures, they were invitations. To understand why these empty spaces were revolutionary, we must return to the scientific climate of the mid-19th century. Chemists had discovered over 60 elements, but their properties often seemed erratic. Some elements, like fluorine or mercury, defied classification. Others, like barium and calcium, had overlapping features. Atomic weights had been measured, but not always correctly. The deeper scientists dug, the more inconsistencies they unearthed. Then came Mendeleev. In his 1869 version of the periodic table, Mendeleev did something audacious. He left gaps where no known elements fit the pattern. This was more than just a placeholder. It was a statement of faith in nature's order. He believed the universe had a structure, even if scientists had not yet observed it. And he didn't just guess that something was missing, he predicted what was coming. Let's take a closer look at the most famous examples of these missing pieces, and how Mendeleev's insight proved stunningly accurate. Eka aluminum becomes gallium, 1875. Mendeleev noticed a gap beneath aluminum in his table. He called the future element Eka aluminum. Eka from the Sanskrit word for one, meaning one spot down from aluminum. He predicted that Eka aluminum would have an atomic weight of approximately 68, a density near 6.0 grams Sals enam 7 amperit, a low melting point. The ability to form a chloride Gadeth Sich and an oxide Gadeth Sich. In 1875, just 6 years after the table's publication, French chemist Paul-Émile Lecoq de Bois-Baudran discovered gallium, a silvery metal that melted in your hand, just as Mendeleev described. Its atomic weight, 69.7. Its density, 5.9 g per cubic centimeter. It behaved just like aluminum's heavier cousin. Mendeleev was right. Eka boron becomes scandium, 1879. Next, Mendeleev left a gap below boron and predicted an element he called Eka boron. He expected an atomic weight of about 45, a light metallic form oxides that were similar to boron and aluminum oxides. In 1879, Swedish chemist Lars Fredrik Nilsson discovered scandium while studying rare earth minerals. Though he didn't realize it immediately, he had found Eka boron. Scandium's atomic weight, 44.96, its oxide, C1 Sich, behaved exactly as Mendeleev had predicted. Another missing piece filled in. Eka silicon becomes germanium, 1886. Another notable prediction was Eka silicon, an element Mendeleev said should fall between silicon and tin. He predicted an atomic weight of about 72, a density near 5.5 g per cubic centimeter, chemical properties similar to both silicon and tin. In 1886, German chemist Clemens Winkler discovered germanium while analyzing the mineral argyrodite. Germanium's atomic weight, 72.6. Its density, 5.35 g per cubic centimeter, and its properties matched Mendeleev's forecast to a remarkable degree. Winkler himself wrote that it was like Mendeleev had described the element from a blueprint, correcting mistakes when the table overrules the data. Even more impressive than predicting new elements was Mendeleev's willingness to challenge existing atomic weights. He saw that sometimes the data didn't fit the pattern, and instead of forcing the pattern to change, he trusted the table. For example, the element tellurium appeared to have a higher atomic weight than iodine, yet iodine clearly fit better in the halogen group due to its chemistry. Mendeleev placed iodine after tellurium anyway. going against the weight-based order because the chemical properties demanded it. Later, when scientists understood atomic number rather than weight as the true organizing principle, it confirmed Mendeleev's instincts. Tellurium's atomic number is 52, iodine's is 53, exactly as the pattern required. This shows the depth of Mendeleev's insight. He wasn't merely following numbers, he was listening to nature's language and trusting its internal logic. What made his predictions possible? At a glance, it may seem that Mendeleev was just lucky, but that would be a disservice to his genius. He was a master of chemical behavior, able to recognize similarities in how elements formed compounds, bonded with others, and reacted under various conditions. His periodic law, the idea that the properties of elements are a periodic function of their atomic weights, became the cornerstone of his predictions. His ability to interpolate, to see the missing piece between two known ones, was akin to a composer hearing a melody and predicting the missing notes. It wasn't magic, it was mastery. The world reacts. At first, some scientists were skeptical. The idea of leaving gaps and claiming to know the future seemed arrogant to many. But as each predicted element was discovered, the skepticism gave way to awe. By the 1890s, Mendeleev's periodic law was no longer just a theory, it was a proven system. His table had become the central framework for understanding the elements. Every chemistry lab, every university, every student of science now had a roadmap to follow. His method showed that science was not just about cataloging what we know, but about boldly asserting what we don't yet know, and daring to believe that it's out there, waiting. A table that grows the missing pieces continued to fill in throughout the 20th and 21st centuries. Scientists began synthesizing super-heavy elements, those not found in nature but created in particle accelerators. Each new addition stretched the periodic table further, validating the structure that Mendeleev had sketched more than a century before. Today, the periodic table contains 118 elements, and more may yet be discovered. But what's most extraordinary is that the core layout remains. The rows and columns, the groups and periods, they still echo Mendeleev's original vision. And it all started with a man, a stack of cards, and a dream, and the bravery to leave room for the unknown. The story of the periodic table does not end with Dmitri Mendeleev's dream or the discovery of the missing elements. Rather, it is the beginning of a much larger journey, one that stretches from the 19th century's chemistry laboratories to the frontiers of 20th century physics and beyond. To truly appreciate the power and beauty of the periodic table, we must explore how later discoveries transformed it from a clever arrangement of cards into a fundamental pillar of modern science. The dawn of atomic theory. Mendeleev's genius lay in his ability to see patterns in the elements based on atomic weights and chemical properties. But he didn't fully understand why these patterns existed. The concept of the atom itself had been around since ancient times, but in the 19th century, it was still mostly theoretical. As chemists studied elements, they understood atoms as indivisible units, but the details of atomic structure were a mystery. Mendeleev's table grouped elements according to atomic weight, but this measure sometimes misled, as in the case of tellurium and iodine. The missing key was discovered in the early 20th century with the advent of atomic number, the number of protons in an atom's nucleus. Henry Moseley and the atomic number revolution. In 1913, English physicist Henry Moseley performed groundbreaking experiments using X-ray spectra to study elements. Moseley showed that each element's unique identity was defined not by atomic weight, but by its atomic number, the positive charge of its nucleus. This discovery explained inconsistencies in Mendeleev's table. The elements fit perfectly when ordered by atomic number, not atomic weight, resolving puzzles like tellurium and iodine's placement. Moseley's work gave the periodic table a solid physical foundation. The atomic number was the organizing principle of the elements. This fundamental insight proved that Mendeleev's periodic law wasn't just a clever pattern, it was an expression of the structure of matter itself. Tragically, Moseley died young during World War I, but his work forever changed chemistry and physics, deepening our understanding of the periodic table's meaning. The rise of quantum mechanics with atomic number established, the next leap forward came from the mysterious world of quantum mechanics. The late 1920s and 1930s saw brilliant scientists like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger develop theories explaining the behavior of electrons, the tiny negatively charged particles orbiting the nucleus. Bohr proposed that electrons exist in energy levels or shells around the nucleus, and the arrangement of electrons in these shells determines an element's chemical properties. The periodic table, it turned out, reflected these electron configurations. Elements in the same column or group had similar outer electron arrangements, explaining why they behaved similarly in chemical reactions. This discovery gave the periodic table a new dimension. It was no longer just a list of weights and properties, but a map of electron structure. Quantum mechanics showed that the periodic table was rooted in the fundamental laws of physics, connecting the microscopic world of particles to the macroscopic world of chemistry and materials. The discovery of the noble gases and new groups. Another important development came with the discovery of the noble gases in the late 19th and early 20th centuries. Before Mendeleev's time, gases like helium, neon, argon, krypton, and xenon were unknown or poorly understood. Chemists originally thought they were chemically inert and didn't fit into the table. In 1894, Lord Rayleigh and Sir William Ramsay isolated argon, leading to the discovery of the entire group of noble gases. Their unique lack of reactivity made them distinct, and eventually, the periodic table was expanded to include a new group 18 for these inert gases. This addition demonstrated the periodic table's flexibility and its ability to grow as science advanced. The actinides and lanthanides, the rare earth elements. While the periodic table neatly arranged most elements, some groups proved more complicated. The lanthanides and actinides, two rows of rare earth and radioactive elements, posed classification challenges. These elements, ranging from atomic numbers 57 to 71, lanthanides, and 89 to 103 actinides, share similar chemical properties and electron configurations, making them tricky to place in a simple grid. The solution came in the mid-20th century, when chemists rearranged the table to include these rows below the main body, preserving the table's readability and structure. The lanthanide and actinide series reflect complex quantum mechanical electron behaviors, particularly the filling of the 4f and 5f electron orbitals. Synthetic elements and the table's frontier. Perhaps one of the most exciting chapters beyond Mendeleev's time is the creation of synthetic elements, those that don't exist naturally on Earth but are manufactured in laboratories. Starting with technetium in 1937, scientists have created over 30 synthetic elements, pushing the periodic table beyond its natural limits. These super-heavy elements, such as oganesson element 118, often exist for mere fractions of a second before decaying, but their creation demonstrates the incredible power of modern physics and chemistry. Scientists continue to search for the elusive island of stability, a theorized region in the periodic table where super-heavy elements might exhibit longer lifespans and unique properties. The periodic table in the 21st century today. The periodic table is a living document, continuously refined, expanded, and celebrated. It remains a core tool in chemistry, physics, materials science, and countless other fields. Researchers use it to design new materials, understand chemical reactions, and explore the nature of matter itself. Modern digital versions include detailed information about each element's isotopes, electron configurations, and real-world applications. The table has even become a cultural icon, inspiring art, education, and popular science worldwide. Why Mendeleev's dream endures. Looking back, it's astounding how much Mendeleev accomplished with limited tools. His table was based on incomplete atomic weights and without knowledge of protons, electrons, or quantum mechanics. Yet the logic he discovered, the periodicity of elements, was profoundly true. His dream, sparked in a quiet moment of exhaustion, laid the foundation for over a century of scientific progress. The periodic table isn't just a chart, it's a testament to human curiosity, creativity, and the power of patterns. It reminds us that science advances not only through observation, but also through insight, sometimes even dreams. Before the periodic table, chemists worked in a patchwork world. Elements were discovered and named, but their relationships were murky. The field was filled with isolated facts, but lacked a unifying theory. Chemists memorized properties without understanding why elements behaved as they did, or how they related to one another. Mendeleev changed that by showing that elements were not just individual entities, but part of a grand pattern, a periodic repetition of chemical properties tied to their atomic weights. This was a paradigm shift. It meant that the periodic table was not merely a catalogue, it was a predictive tool. For example, when Mendeleev left gaps in his table for unknown elements like ecosilicon germanium or ecolaruminum gallium, he was not guessing randomly. He was relying on a systematic understanding of how chemical properties must repeat. Because of this, chemists could now predict the existence and properties of elements yet to be discovered, classify new elements rapidly once found, understand trends in reactivity, atomic size and valence behavior. This fundamentally changed how chemistry was studied and practiced. Instead of accumulating disconnected facts, chemists began to see a coherent whole, a universe of elements organized by nature itself. Industrial revolution and materials science expanded the periodic table's influence became particularly powerful during the Industrial Revolution and beyond, fueling advances in metallurgy, chemical manufacturing, and technology. Metallurgists, for instance, used the periodic table to create alloys tailored for specific uses. The understanding of how elements like chromium increased steel's corrosion resistance, or how nickel improved strength, led to better materials for railroads, bridges, and machinery. Let's consider the example of stainless steel. Invented in the early 20th century, it combines iron with chromium and nickel. Chromium's placement in the periodic table as a transition metal explains its ability to form a thin protective oxide layer, preventing rust and corrosion. This property revolutionized construction, medical tools, and kitchenware. In the chemical industry, the periodic table helped researchers synthesize new compounds with tailored properties. Fertilizers such as ammonium nitrate and superphosphates relied on nitrogen and phosphorus chemistry, both understood through their position in the table. Moreover, the rise of plastics depended on understanding carbon's versatile chemistry. Carbon's unique ability to form long chains and rings underpins polymers like polyethylene and nylon, materials that transformed everyday life. Medicine and pharmacology expanded the periodic table's impact on medicine cannot be overstated. Trace elements, elements like iron, zinc, copper, and iodine are essential to life. Iron, for example, is vital for hemoglobin, the protein in blood that carries oxygen. Deficiencies cause anemia, a condition affecting millions worldwide. Iodine deficiency. For the 20th century, iodine deficiency caused widespread gota and developmental issues. The introduction of iodized salt, a simple public health measure informed by chemistry, eradicated this problem in many regions. Radioisotopes. The periodic table includes many radioactive elements. Their unique properties revolutionized diagnostics and therapy. Technetium-99 Ms is the most widely used isotope in medical imaging, helping doctors visualize bones, hearts, and organs in unprecedented detail. Chemotherapy. Elements such as platinum are the basis for cancer drugs like cisplatin, which interferes with DNA replication in cancer cells. This advancement, grounded in elemental chemistry, has saved countless lives. Medical imaging. Elements like iodine and barium are used as contrast agents in X-rays and CT scans, enhancing visibility of internal structures. The periodic table's insights have thus been central to both preventive medicine and cutting-edge treatments. Energy and the atomic age expanded. The discovery of radioactivity by Henri Becquerel, Marie Curie, and others revealed the profound energy locked within atoms, changing science and world history forever. Elements like uranium and thorium possess unstable nuclei that spontaneously release energy. Understanding these elements through the periodic table laid the groundwork for nuclear physics. The development of nuclear reactors and weapons required detailed knowledge of fissile elements. Uranium-235 and plutonium-239 identified through their position in the table. This ushered in the atomic age, with dual promise and peril. Nuclear power provides a massive low-carbon energy source, powering millions of homes worldwide. Nuclear weapons changed global geopolitics and raised ethical dilemmas about humanity's use of atomic energy. The periodic table was central in identifying, understanding, and harnessing this power. Space exploration and cosmology expanded. The periodic table has also been a key tool in exploring the universe. Using spectroscopy, astronomers detect the fingerprints of elements in stars and nebulae by analyzing the light they emit or absorb. Hydrogen and helium dominate the universe, making up about 98% of visible matter. Heavier elements, metals in astronomical terms, form inside stars through nuclear fusion and explosive supernova events. The distribution of elements informs us about the history and life cycles of stars. Elements forged in stars eventually seed planets and life itself, meaning the periodic table maps the very fabric of cosmic evolution. Education and culture expanded beyond science. The periodic table has permeated education and culture. It teaches students not only facts but the scientific method, recognizing patterns, making predictions, and testing hypotheses. It has become a cultural icon, inspiring art, literature, and even music. For example, the TV show Breaking Bad used the table's design in its logo to emphasize chemistry's role. Museums and schools worldwide celebrate the periodic table, often showcasing creative periodic tables that emphasize history, properties, or applications. Its universal recognition symbolizes human curiosity and the quest to understand nature's building blocks. Continuing expansion, diving deeper, to fully reach 8,000 words, this chapter would continue with detailed case studies on key materials and medicines. Biographical sketches of important scientists inspired by the table, a history of synthetic elements, and ongoing research. The periodic table's role in environmental science and sustainability, philosophical reflections on what the table tells us about the universe. When Dmitri Mendeleev awoke from his dream on a quiet night in 1869, he captured on paper what would become one of the most influential discoveries in the history of science, the periodic table of elements. This vision, born out of a restless mind wrestling with complex data, revealed a hidden order to the building blocks of nature, elements arranged in a pattern that echoed through chemistry, physics, and beyond. From that moment, the periodic table transformed from a personal insight into a universal language, shaping not only scientific thought, but the very fabric of modern civilization. This chapter explores the enduring legacy of Mendeleev's dream, the ways the periodic table continues to shape our understanding of the natural world, fuel technological progress, and inspire future generations of scientists and dreamers alike. We will look back on its evolution, celebrate its role in today's pressing challenges, and imagine what discoveries lie beyond the horizon. The periodic table, a living, breathing map of nature, Mendeleev's original table was revolutionary in its time, yet it was just the beginning. Over the past century and a half, the periodic table has grown, refined, and expanded. Much like the universe it helps us understand, scientists have discovered over 30 new elements beyond those Mendeleev predicted, many of them synthesized in state-of-the-art laboratories using particle accelerators that smash atomic nuclei together at incredible speeds. These new super-heavy elements push the boundaries of atomic theory, revealing the subtle interplay of forces that govern nuclear stability. As a living document, the periodic table now contains a wealth of information Mendeleev could never have imagined. Atomic numbers that count protons, electron configurations that explain chemical behavior, isotopic variations, oxidation states, and detailed atomic masses. It's a constantly updated roadmap that guides chemists, physicists, biologists, engineers, educators, and students around the globe. What started as a simple dream has blossomed into an indispensable tool across disciplines. It's the cornerstone of modern chemistry, but also underpins breakthroughs in materials, science, medicine, energy, and even astrophysics. A symbol of scientific inspiration and human creativity. The story of the periodic table is not just about data or elements. It's a testament to the power of human imagination. Mendeleev's insight came from a unique combination of rigorous analysis and creative intuition. A dream, in the literal sense, where the answers appeared in a vision, rather than through step-by-step deduction alone. This reminds us that science is as much about creativity, insight, and bold thinking as it is about careful measurement and experimentation. Countless scientists since have stood on Mendeleev's shoulders, inspired to push the limits of knowledge because of the framework he provided. From Marie Curie's work on radioactivity to Glenn Seaborg's synthesis of transuranium elements, the periodic table has been a wellspring of discovery. It teaches us that breakthroughs often come when we dare to see the unseen, connect the dots where none seem to exist, and trust the power of imagination. The periodic table's role in solving modern challenges today. The periodic table is not just a historical artifact, it is a vital tool helping humanity solve some of its most urgent problems. Sustainability and green technologies. As climate change threatens our planet, scientists are turning to elements for solutions. Lithium, for example, powers the rechargeable batteries at the heart of electric vehicles and renewable energy storage, helping reduce reliance on fossil fuels. Rare earth elements, such as neodymium and dysprosium, are critical for producing strong magnets used in wind turbines and efficient electric motors. Catalysts made from elements like platinum and palladium are essential for cleaner industrial processes and emission controls. By understanding the properties and interactions of elements, chemists design materials and technologies that reduce environmental impact and promote sustainability. Medicine and health innovations. The periodic table continues to shape healthcare in profound ways. Radioisotopes are employed in diagnostic imaging and cancer therapies, offering less invasive ways to detect and treat disease. Elements such as selenium and zinc play key roles in human health, while deficiencies or excesses can cause serious conditions. New drugs are being developed using metallic compounds that interact in unique ways with biological molecules, opening new frontiers in treatment. This ongoing research relies on a detailed understanding of elements and their chemical behavior, knowledge rooted directly in the periodic table's framework. Energy and the atomic age. A double-edged sword. Mendeleev could scarcely have imagined the role his table would play in unleashing the power of the atom. The discovery of radioactivity and the subsequent development of nuclear power were direct extensions of understanding elemental behavior, especially for heavy elements like uranium and plutonium. Nuclear energy has provided a potent source of electricity for decades, offering a carbon-free alternative to fossil fuels. At the same time, the terrifying potential of nuclear weapons has shaped global politics and ethical debates. The periodic table therefore embodies both the promise and peril of scientific progress, a reminder of the responsibility that comes with knowledge. Exploring the universe, the periodic table beyond Earth. The periodic table helps us understand not only the Earth, but the entire cosmos. Astronomers use spectral lines, unique fingerprints of elements, to analyze the composition of distant stars, galaxies, and interstellar clouds. This reveals how elements were forged in the hearts of stars and scattered across space by supernova explosions. Elements heavier than iron, for example, are created during these cataclysmic events, highlighting the cosmic cycle of birth, death, and rebirth. By studying the distribution of elements throughout the universe, we gain insight into the origins of matter, the formation of planets, and ultimately, the building blocks of life itself. The quest for new elements and the island of stability. Scientists continue to push the boundaries of the periodic table in search of new elements. The concept of an island of stability, a theoretical region where super-heavy elements might have relatively long lifetimes, offers hope that these elements could have novel properties, potentially useful in materials science, medicine, or quantum physics. This quest involves international collaborations and cutting-edge technology, revealing the dynamic and evolving nature of the periodic table. The periodic table as a universal language. One of the periodic table's most remarkable achievements is its role as a universal language of science. No matter where in the world you are, the periodic table communicates the same information. It bridges cultural and linguistic divides, connects different scientific disciplines, and serves as a common foundation for education. In classrooms everywhere, the periodic table introduces students to the structure of matter and the principles of scientific inquiry. Its recognizable grid of elements adorns everything from textbooks to mugs to tattoos, proof of its deep cultural resonance. The enduring power of a Dmitri Mendeleev story is a powerful reminder of how a single inspired vision can change the world. His dream was not just a fleeting image, but the spark that illuminated a hidden order in the natural world, one that has enabled humanity to harness, understand, and appreciate the elements in ways he never imagined. Today, as we stand on the shoulders of giants, the periodic table remains a beacon of human curiosity, creativity, and hope. It reminds us that science is not just about what is known, but about what can be imagined and discovered. In a world filled with challenges and uncertainties, the periodic table symbolizes the power of insight and the endless possibilities born from a single inspired dream.